Hello and welcome to my 5th physics lab presentation. For this lab, I chose to observe the motion of a stretched slinky drop from static equilibrium, meaning it had an initial velocity of 0. The goal of this lab was to understand what and how different forces affect the slinky's motion and create a computational model based on that knowledge. At the end of the lab, I was able to make a model similar to the observed motion with a few discrepancies. To analyze the motion of the slinky, I used the bottom of the slinky as reference for position points in Tracker. I found the initial position but chose to ignore the x and z component of the position as we are only focused on the vertical motion of the slinky. In Tracker, we used Derek Mueller, who is on the left for distance height calibration. Since it was dropped and not thrown, we assumed the slinky had an initial velocity of 0. I also gathered the standard mass of the slinky for later use in our computational model. Before diving into the code, let's look at the fundamental principles needed to create the model. We assume there are 3 forces acting on the bottom of the slinky as it is dropped from rest: gravitational force, drag force, and the tension from the top of the slinky, since we are only looking at the motion of the bottom of the slinky. Gravitational force on Earth can be calculated using mass times gravitational acceleration on Earth, which is approximately 9.8 meters per second squared. The particles in the object's atmosphere interact with the object itself and is represented by drag force. There is also tension coming from the top of the slinky, since it's connected to the bottom of the slinky and exerts a force on the bottom, which we will see is equal and opposite to the gravitational force. Finally, we'll be using Newton's second law to calculate the velocity and position of the slinky at a given time. These portions of the code showed the given information from Tracker and also known variables. I also found the drag proportionality constant by trial and error. As we can see by the constant, drag force will not affect the slinky greatly. At the heart of the code are 2 while loops, the first representing the time in which the slinky was falling and starting to recoil, in which case only the tension from the top of the slinky and gravity were the forces acting on the bottom of the slinky. Then we used what we know about fundamental principles discussed in the previous slide to obtain velocity and position points. The second while loop is similar code-wise, except that we replace tension with drag force, because after it completely recoils, the bottom and top move as one, but the slinky experiences slight drag. But overall, the gravitational force overcomes drag force, which is why it starts moving down after it recoils. This graph represents the motion of the bottom of the slinky as it fell. The horizontal part of the lines represent where the bottom of the slinky remained motionless because the tension and gravitational force canceled each other out. The latter part of the graph are where the bottom of the slinky started falling down after the slinky was fully recoiled. Towards the end of the blue line, we can see a horizontal line, which can be attributed mainly to extra points plotted even after the slinky reached the ground, which is why that discrepancy at the end is large. And then this is the simulation created from the code. The results from the graph showed that the tension from the top of the slinky had equal magnitude to the gravitational force, but acted in the opposite direction, resulting in the bottom of the slinky being in equilibrium until there was no more tension. It started moving after because of the large gravitational force, as mentioned before, on the slinky despite the drag force. In comparing the graphs, I can confidently say that I created a fairly accurate model, although discrepancies could be largely due to the following: human error in plotting points on Tracker, and also forces that might not have been included in the model. If I were to redo the lab, I'd be more careful in recording position points on Tracker, and maybe compare the motion of the top and bottom of the slinky. Thank you.